Hi, this is Ideal Gas Law Part 3. So in this video, we are going to take a look at the formulation of the formulation of the ideal gas law that we usually find in the books. So in videos 1 and 2, I've introduced to you that the ideal gas law is formulated like this. So pressure times the volume divided by the number of moles and the temperature of the first state will be equal to the pressure of the second state times the volume of the second state divided by number of particles in the second state and the temperature of the second state. So this is kind of the formula. However, notice that if I change everything, right? If I change the P into another state, then I can also change the V into another state, the N into another state. So this could keep on changing and changing and changing. But notice that whatever the change is, I could go on to 4 states like this. Notice that whatever the change is, they are always equal. So what does that mean? That means that this is equal to that, is equal to that, is equal to that. So meaning whatever value this is equal to that value, is equal to that value, is equal to that value. Meaning it must be equal to the same value, and that value will represent that with an R. An R is what we call a gas constant. Again, let me reiterate that. If P1 V times V1 over N1 equals T1 is equal to P2 V2 over N2 times N2 times T2, then no matter what change I can do to the volume, pressure, N and 3, they will always be equal. And therefore, they have to come up with a constant number. Okay? And that constant number is called the gas constant, or R. Now, there are many versions of constant numbers. I mean, gas constants, there are many versions of it. There are many values of it. But if we are using, for the pressure, if we are using the unit ATM, which is atmosphere, and then for the volume, if we are using liters, and then for the number of particles, obviously we have to be using moles, right? And then the temperature, we have to be using Kelvin. So if we use this one, there must be a constant, and that constant should have these units: ATM, liter, mole, Kelvin. And in fact, when scientists studied this, they found out that the value is this: 0.0821 ATM liter per mole Kelvin. Okay. Again, sir, I did not get that. What is this number here? That number is always the number that equals to this. So if you multiply P times V divided by the N and T, it will always equal like this. You can't change the values of the system, but when you divide, it will always end up like this. So therefore, the most common formula that books follow is this: P, V, and T equals R. Okay, and that R again is a fixed value. It is a true constant, so it's a constant. It doesn't change. Now that number is 0.08206 if you wanna 205 or 206, but in our books we just round it off to three significant figures. So 0.0821 ATM liter mole Kelvin. Okay, so that's the constant value. And the good thing about this is that means you don't have to remember everything. You just have to remember this number, and you just have to remember that whatever the value of P is, multiply it with a V, divide it with the N, divide it with the multiplication between N and T, you will always get that number. And this number is a true constant. This number is a true constant, meaning it really never changes. No matter what the temperature is, No matter what the number of particles is, no matter what the volume is, no matter what the P is, this is always the constant for all ideal gases, which is 0.08205. But again, we round it off to three significant figures. So 0.0821 atm liter mole Kelvin. Now, obviously, I could also use instead of ATM, I could use pascals, which is the kind of preferred unit. And then for liters, I could also use meter cube. In that case, you will end up with another value of R, which is this one. That would be 8.314 joules per mole Kelvin. And it becomes like that because remember your uh, your pressure is in pascals, right? And your volume is in meter cube. Your pressure is in pascals, and then your number of moles is still mole. Your temperature is still Kelvin. But if you remember, Pascal is also Newton per meter cube. Squared. Newton per meter squared. So therefore, if you multiply that meter cube times Newton per meter squared divided by mole Kelvin, notice that this meter squared gets cancelled out. It now becomes, and this meter cube becomes only meter. So Newton meter is joule. So that's why it becomes mole Kelvin. But again, uh, these are just two of the common values of R. Again, the key here is to understand if you're using liters, if you're using atm for the pressure, liter for the volume, moles for the N, and Kelvin for the temperature, you will have this value, 0.0821 atm liter mole Kelvin. But if you use meter cube for the volume and then Pascal for the pressure, you will end up with another unit called joule per mole Kelvin, and it has another number, 8.314. So again, there are different versions. If you are using, for example, if you would not use Pascal or ATM, if you would use another unit of pressure, then this whole value changes. But the standard is using Pascal, using ATM and liters, which means this is the standard value, which is 0.0821. And the second most commonly used is this one, 8.314 joule mole Kelvin. But again, the most common one is this one. And again, this is also what is used in the grade 10 learners material. So I would slightly lean into this value. And again, there are many versions, and I don't want to confuse you with a lot of stuff. What is important is that you understand that when you change the values here, it becomes state number 2. No matter what the configurations of the pressure, volume, number, particles, and temperature is, when you do the calculation, you will end up with this, as long as you're using atm, liter, mole, and Kelvin. Okay, so you will end up with this value, which is 0.0821 atm liter mole Kelvin. Okay, so again, even if I kind of alluded to you, I kind of suggested to you that this really P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. What is really preferred by books is this format, which is PV over NT equals R, right? So this is the most common variation, and in some books they would even do it as PV equals nRT because it's kind of easy to remember like that. But I really like this idea because if you have this, it's kind of easy to remember that this came from that, right? And it's easy to tie up with the other values, right? And again, R here has a certain fixed value, and that fixed value is again 0.0821 if you're using ATM, liter, and then mole and Kelvin units. Okay, so that is the idea for the ideal gas law.